All right, so I want to talk, we're going to wrap up those last few examples on that PDF. So, all right, so on some of these guys, what my concern is that we not necessarily maybe know the steps. Because I think we already know the steps. But I want to talk about why we do those steps and what becomes important. Because eventually, you're going to see the necessity of understanding why we did something so that you can kind of adjust the way you're thinking about it in a certain question so that you can address it, okay? So the other day, we finished, I think, with this one, right? And what we were able to do, because this is one ratio on the left and one ratio on the right, we were able to cross multiply, get those products, and it turned into a linear equation, right? Okay. All right, I guess it's already a linear equation, but maybe it doesn't look that way to you. But if I look at example 6, example 6 is not the same format as example 5, right? At least not at the onset, okay? So the question is, well, how do I approach this? And a lot of people just want to multiply across just like they did. They want to take this 3. I get this so often. People take the 3 and they multiply it by the 2x plus 1, write that down, 6x plus 3. Take the 3 times this, get 3x minus 12. And then they say, okay, not sure what to do, so I'll put equal sign. I'll go 10 plus 12, okay? You can't do that. That doesn't make sense because it's not a proportion, right? So there are no extremes and means here. If you wanted to use that technique, you would have to condense those, all right? You would have to merge those into one fraction, okay? Because this is representing some quantity, you know. So let's say x was, just to make things easy, let's say x was 0. This would be 1/5 plus negative 2/3, right? Okay, and ask if that is equal to 2/3. It's not, but that's kind of the idea of what's going on. You got two fractions being added together to give me that one fraction. So if I want to cross multiply, I need this to be one fraction. So here's an option. What would be the LCD there, or what would be the common denominator, yes, so I can combine those two things? 30, right? Okay. So I'm going to multiply this one by 6 over 6 to make that a 30 in the denominator, right? And then multiply this one by 5 over 5, okay? Now, whether you write this down, I'm going to show you a different technique that is probably quicker. But if you wanted to use cross products, this is what you got to do. So it's going to be 12x plus 6 over 30 plus then 5x minus 20 over 30 is equal to now 2/3, correct? Now I can add this stuff together, so now I get 17x minus 14 over 30 is equal to 2/3. Now it looks like example 5 did, and now you cross multiply and get 51x minus 42 is equal to 60, okay? That's an option, okay? And you can solve that and go through and get the right answer. But I don't necessarily like that because I think it's more work than what's necessary, okay? Because it's an equation, and we've got 3 parts here, why not go through and just find the LCD and multiply every single term, every single part of that equation by the LCD? So what is the number, the lowest number, that each one of these 5, 6, and 3 will divide into evenly? 30. So I multiply this one by 30, that one by 30, this one by 30. And here's what's really going on, is that 30 is 5 times 6 here, right? Does that 5 and that 5 turn into essentially a 1 over 1? So they cancel out, I'm left with 6 times 2x plus 1. So there's the 12x plus 6 that I found earlier, right? Here, this 30 is 5 times 6 again, so the 6 is now canceled. I'm left with 5 times x minus 4, so it's 5x minus 20 And now here, this 30 is 3 times 10. So the 3's cancel. Gives me 2 times 20. So we get that. Okay. And I'll leave it at that stage for you guys to solve for x. But you should get the exact same x that we went and got, or should have gotten through the first method. But my hopes are, as you see it, that's maybe a little bit quicker, isn't it? Okay. The only thing that you got to be cautious of is when I am multiplying this first ratio by 6, that I distribute it. And over here I distribute that 5. Okay? I get a lot of people that don't do that. You also have to be very cautious of what that symbol right there is. Because it might not be a 5 that you're multiplying through. It might be a negative 5 that you're multiplying through. Okay? So just be careful. Is that all right? Okay. So, I want to go to example 7 because it's very similar, but now what is different with 7 is that now where do your variables show up? They show up in the denominator, okay? And a lot of times when our variables show up in the denominator, it provides something that's a little bit more difficult to work with, okay? And the last one we multiplied by 30, the LCD. Well, we could have multiplied by 60. We could have multiplied by 120, okay? We could have multiplied by any common denominator that we wanted to, okay? And just to give you, like, maybe what some people will do is they'll say, well, 5 times 6, that's 30, times 3 is 90. And they'll use 90. It works, it's fine. It's gonna make your coefficients bigger, but it's nothing that we can't do. When I get down to something like this, when I've got variables in my denominator, and I got variables as part of my common denominator, you're not going to want to just use any basic common denominator because it could be very problematic to the new equation that you develop. Okay? And what I mean by that, if I just look at this, okay, 2 times 9 is 18, right? 18 times 18 is 324. 324 times 3 is 972. Okay? You could probably use I know you can use a much smaller coefficient. Let's just go with 972. And then I look at this, well, x shows up, x, so maybe my LCD is x squared. So I multiply all those denominators across, I get 972 x squared. If I use that as my common denominator, and I start multiplying that thing by it, some x's cancel out, right? And I'd be left with x to the first in the first term, okay? Well, then over here, that 9 and the 972, there's going to be a factor there that cancels out, okay? But are there going to be any x's that cancel out? No. So that term's going to be quadratic. It's going to be x squared. Same thing here. It's going to be x squared. And they're not going to be the same, so they don't cancel, because one's on the left-hand side, one's on the right side. They won't cancel each other out. We'll have to add them together or subtract them, whatever. And then this one will give me x. So what that develops eventually, if I use that common denominator, it develops a quadratic equation. For quadratic equations, things that are x squared, harder to solve than linear equations? Yeah. So if I can avoid doing that, I want to. Okay? Now I should end up getting the same answers if I did that correctly. If I know how to factor something x squared. However, it's going to be more time consuming. I'm probably going to get solutions that I have to check, because one of them's probably not going to work. Okay? So, the best thing to do, guys, is to find the LCD. Okay? Now I'm going to show you why we do it this way. Okay? Or I guess the tools or the strategy for finding the LCD is that you take your denominators and you factor them. You find the prime factorization of every one of them. Okay? I'm going to venture to say that we can all look at that and say 18 has to be the coefficient. Anybody disagree with that? So I can make the 2 turn into 18, I can make 9 turn into 18, 18 is already 18, and 3 can turn into 18 as well. So that's going to be the coefficient. But sometimes that's not as easy for people to recognize. So this is what we really do. We take every one of these fractions and we do the prime factorization, meaning that we break them down to the product of all prime numbers. Any number that you ever come across, can be written as a product of prime numbers. Okay? So we're going to do that. So the 18 is 2 times 3 times 3. We have 1 times 3 times that. And it's going to be very important when we get to even more complicated, complex-looking denominators. I'm going to rewrite this as obviously 5 divided by 2 times x. This I'm going to rewrite as 8 divided by 3 squared. 2 times 3 squared. Now, a lot of this, guys, you would probably not write down, okay? I want you to make sure that you see what we're doing here. When we choose the LCD, the rules for choosing an LCD is that you always have to pick new factors, okay? And if a factor repeats, does anybody know which ones you choose? If it repeats and it has different or varying powers, does anybody know which one we choose? So if I look at this, we've got a 3 to the first, right? Over here. And here we got a 3 squared. Which one do I choose? The largest. I use 3 squared. Because I need that 9 to show up, right? If I don't choose the 3 squared, the 9 will not show up. Okay? So, going through here, I just start kind of check marking the things that I know need to be in my LCD. 2 is new because it's the first term I come across, so that's got to be in there. X, is that new compared to 2? So X has got to be in there. Is 3 new compared to these two things? Absolutely. So 3's got to be in there. And because 3 squared is new, the 3 squared's got to be in. I'm going to go through here and see if there's any powers of 3 that are bigger than 2. And there's not, right? So I know 3 squared is going to go. Does this 2 go? Do I need to put that in there? No, I've already got it right here, right? It's not new. Does this 3 squared go? No, it's not new. Does this 3 to the first go? No, it's not new, right? Because that 3 to the first is encapsulated right here in this 3 squared. Does this x go? No, it's not new. X is right there. Okay. So now I've decided what my factors or my denominator are going to be. 2 times x times 9. So my LCD is 18x. Okay. Probably something we could have gotten to without the 5 or 6 minute discussion. But later on, when those denominators become much more kind of convoluted and ugly, you have to go through that process. Okay? You're not going to want to just multiply them all together and get a common denominator, because that might turn your equation into a quartic. Do we know how to factor a 4th degree polynomial? Or a quintic, a 5th degree polynomial? We don't have those tools yet. Okay? And even once we do have those tools, none of us are going to want to do that. Okay? It's the pain in the butt. All right. So now we're going to multiply every one of these things by 18x. 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 So how do the 18x and the 2x, how do they cancel each other? What are they going to leave me with? Does everybody understand or know that this is 18x times 5 over 2x? And that 18x can be written as 2x times 9 times 5 over 2x, right? Now what happens with 2x's? It's a factor of 1, isn't it? Cancel each other out. Okay? So that's why right here we just do 2x and 18x, divide out, give me 9. 9 times 5 is what is left there, just leaves me 45. I think a lot of times in Algebra 1, Algebra 2, we go through these procedural things, but we don't necessarily understand why we're doing it. Maybe we see it 1 or 2 times at the beginning of the class, or the beginning of the lecture, then we get into the procedural thing, and the understanding and the logic of why we do it kind of vanishes. But if we understand that logic and that reasoning, it makes that process really easy, and you're not going to forget, well, what do I do next? Okay? So now here, the 18x and the 9 cancel, leaving me just 2x, right? So I get 2x times 8 gives me negative 16x. The 18's cancel here, just leaving me x. And now this is going to go to just leave me 6, right? And we should now have the ability to go through 51 is equal to 17x. X has got to be 3. Okay. Now I want to show you something, because I told you this yesterday, or Friday, I guess. And every time that we do one of these problems, that there's a graphical rendering that exists in the background that should provide us the solutions. Okay? Now what I want you to understand is that the solutions to this exist as solutions to that. Does that make sense? Okay? Because this is going to be a different graph than what this is going to be. This is going to be a different graph than what that is. But the solutions to this exist in here. Does that make sense? So if the solutions to this exist in here, and the solutions to this exist in there, that means that the solutions to this and the solutions to that should be the same. They should exist within one another. Okay? So I'm going to quickly go to our graphing tool here and just show you what that first one was like. 5 divided by 2x minus 8/9. Okay? So the left-hand side looks like that thing. And that's one of the first rational type equations that we'll talk about. It's called a reciprocal equation. And then I'm going to write in 1 over 18 minus 1 over 3x. So give me the right-hand side of the equation. And we'd be looking for where the green one and the blue one cross, right? And we're seeing those two things cross. Not sure what I did again, fine. Cross right there at B, where the x value is 3, correct? That's what we came up with algebraically. Algebraically, what we're doing is we're taking that rational equation and we're doing this one. We're making the equations a lot easier to deal with, and eventually we're getting something like 51 on the right hand side, and y equals 51, and y equals 17x. And wouldn't you agree that those two graphs are a little bit easier to kind of manipulate and look at and analyze than what the blue and the green one were on the left hand side? Okay? But the solutions of the things on the green graph show up as solutions to the things on the yellow graph. And that's a key thing to understand about all equations. As we start manipulating them, okay, the solutions to the original one show up as solutions to the manipulated ones. And it's the whole idea of balancing equations. Keeping the left hand side the same as the right hand side. Alright, so I think that is always something to keep in the back of your mind. Because you're going to struggle at some point in this class. You're going to say, I got this equation, I don't know how to solve it. Well, what can I always turn to? You can always turn to this and at least get a solution, right? Get an understanding of what the solution should look like. And that might then kind of flip a switch and say, okay, maybe I go through 1, 2, 3 procedures that I maybe not 100% confident, but maybe one of those produces that solution I already know should exist. I'm losing my voice. Okay. So that's important. Let's look at this one. Pretty easy in regards to this. Whereas to the last one, this one should not be too problematic. What should be the LCD there? X plus 4. And this is key, guys. When we see, in the previous one, it was just like a 2x or a 3x or something like that. It was a singular term. Here we have a sum of two objects, right? That's a quantity, okay? But we still view it, and a lot of times maybe we want to put parentheses around it, as one thing. Okay? A lot of times I see people go through and say, okay, I need an x in there and I need a 4 in there. So they say 4x is my LCD. That's not the case because these things, this is one object. Okay? Because remember, x is our unknown, right? Once I know what x is, what does that thing turn into? What does x plus 4 turn into if I know x to be 3? Turns into 7, right? Turns into one singular object. Okay? So that x plus 4 is representing some real number. Okay? So that needs to be part of my common denominator. Okay? And that is actually the only thing that becomes part of my LCD because this is a 1, right? Okay? So I'm just going to multiply everything by x plus 4. X plus 4. X plus 4. X plus 4. So here they just cancel, correct? And when they cancel like that, what am I left with? What numerical value am I left with? When things cancel, what are we left with? We're left with 1, right? Okay? And that's something to think about when we refer to canceling through division or multiplication. We're left with 1, not 0. Okay? So it gives me 1 times 3. Okay? Now here, what am I going to get when I multiply these two things? I heard some 7x plus 28. Okay? Remember that 7 is negative, right? Okay, so this is what this looks like. Or write it out maybe a little bit more explicitly. We have 3x plus 4. We're going to multiply that by x plus 4. And we got minus 7. We're going to multiply that x plus 4. Well, here obviously those cancel out. But now you have negative 7 times this quantity, so don't you always distribute the negative as well? Okay, so it's got to be negative 7x minus 28. What happens with these x plus 4s here? They cancel out. Leave me just negative 4. So we're getting negative 7x. What's that going to need? Negative 25. Add 25 is going to get 29. All right? No. 21. So x becomes negative 3. Okay. And we should be able, every time we do one of these, especially when they're rational, guys, go back in and make sure things work out. Make sure that if I take negative 3, what's 3 over negative 3 plus 4? Well, negative 3 plus 4 is just 1, right? So it just gives me 3 when I plug back in. Minus 7. And then here I get negative 4 over 1. Does 3 minus 7 equal negative 4? Absolutely. Tells me my answer is right. Sometimes with rational equations, guys, just depending on the algebra, you might get extraneous solutions. When I look at this, what do I know? What one number am I not allowed to use in that denominator? What one number can x not be? It cannot be negative 4. Because it would give me 3 over 0, right? We can never divide by 0. Okay? So just keep those things in mind when you start seeing rational equations with variables in the denominator. Same thing kind of goes for this one. Okay? But this one here is the reason I wanted to factor that first one. When we took that, I think it was like 2x in the denominator, we had a 3, and we had a 9, we had an 18x, and we prime factorized that. It's a good idea to do here as well. Okay? Because a lot of people are going to go through this and say x plus 2 needs to be in there, x minus 2 needs to be there. Oh, and x squared minus 4 looks different than those two things, so that's got to be in there. And if we do that, that turns into a 4th degree polynomial that we can multiply as an LCD. And what that ends up doing is giving me a cubic equation. And I should be able to solve that. Solving a cubic equation involves probably maybe long division of polynomials, maybe the synthetic division process or algorithm, rational root theorem. Maybe those are some things you've heard. That's a pain in the butt. Okay? If I factor this initially, do my, I'm going to call it prime factorization. If I do that, doesn't this one on the right hand side turn into x plus 2, x minus 2. Those are the factors, right? So what we always want to do is make sure that when we have these rational equations, that our denominators are factored into their linear terms. Every one of those is now some quantity to the first power. Okay? So now, remember these are quantities, so that has to be part of my LCD, right? Is this new? So that has to be part of my LCD. Is this new? Nope. It's already right there. Is that new? Nope. It's already right there. So even though that looked different at the beginning, when we factor it, it is already the two terms that we have over here. So my LCD is x plus 2, x minus 2. X plus 2, x minus 2. X plus 2, x minus 2. People say, well, why don't you just write it as x squared minus 4? If I write those as x squared minus 4 in red up there, I'm not going to be able to easily decipher what cancels, right? I always want things in their factored form to see what cancels. So, the x plus 2 here, and that x plus 2 should cancel, leaving me 7x minus 14 in. This x minus 2 and that x minus 2 cancel, leaving me 5x plus 10. And now, that is the same as that product there, leaving me then just 10x minus 2. And I think we did this last class. Does that end up giving you 1 as a solution? Okay. So x ends up being 1. Again, if I were to graph those two sides of that original black equation, it's going to be really ugly. I think actually both sides